Now coming to the group 17 and 18 elements, we can say that. So in the group 17 elements in the periodic table, we have got the halogen family. That is your fluorine, chlorine, bromine, and iodine and astatine, which is artificially prepared. We can say that all are natural: fluorine, chlorine, bromine, iodine. But astatine are artificially prepared, and it is radioactive element. They are collectively known as halogens. Why? Because salt producer. Halogens has come from the word halos means salt and genes means bond. So it is salt producer. We can say that. Clear? So now, although the first member of the group, that is a fluorine, differs from other members of the group in several respects, yet halogen shows close resemblance and observe very uniform trends in their physical and chemical properties. This is quite important to note it. That what you find is that halogen shows a close resemblance and observe very uniform trends in their physical and chemical properties. That is, your physical and chemical properties almost same. Got it? So after the alkali metals, we can say that halogens constitute the most homogeneous group in the periodic table. It can come in short question that halogens forms the most homogeneous group after the alkali metals. We can say that means the properties almost remains the same. Since halogens are highly reactive, they do not occur in the native state in nature. They are always found in the combined form, mainly in the form of metal halides. Mainly in the form of metal halides, we can say that, like rock salt, sodium chloride, we can say. Now, you know that fluorine has been a problem of extraction because it's a very strong oxidizing agent. Note it, it's a very strong oxidizing agent. It was successful. That is, Moissan was successful in isolating fluorine in the elemental form in 1886 by an electrolysis of molten mixture of potassium fluoride and anhydrous hydrogen fluoride. Got it? Moissan, Moissan, Moissan as the name of the scientist. He was successful in isolating the fluorine in the elemental form in around 1886. We can say that that is by electrolysis of molten mixture of potassium fluoride Kf and anhydrous hydrogen fluoride HF, where fluorine is being collected at the anode. We can say that when you go for the electrolysis, then hydrogen is collected at cathode and fluorine is being collected at anode. In this way, fluorine was being prepared by Moissan. He was able to do that. Chlorine is generally manufactured by the electrolysis of natural brine or aqueous solution of NaCl. That is, sodium hydroxide and hydrogen are being produced as the byproduct. So we get chlorine, again same thing at the anode. We will see it later on that chlorine is also manufactured by MnO2 and KMnO4. Got it? By using manganese dioxide and potassium permanganate, which acts as an oxidizing agent. Bromine is generally manufactured by the oxidation of Br- ions, a natural brine with chlorine, and iodine is prepared commercially from natural brine or seaweeds by the oxidation of the iodides ion with chlorine. We can say that is the equation. We can say 2I minus plus Cl2 gives I2 plus 2Cl minus. Okay. Now coming to the physical state, fluorine and chlorine are gaseous at room temperature. Bromine is a liquid while iodine is a solid. Iodine is a solid. Alright, the intermolecular forces existing between the molecules are the van der Waals forces. As the size of the atom increases and going down the group, the strength of the van der Waals force also increases from fluorine to iodine. Alright, from fluorine to iodine. Alright, this is why the state of agglomeration, the tendency to form molecules, to come closer and form molecules, increases. Alright, so for that particular reason, as the atoms, when they come closer, got it, and they form an agglomeration of molecules, that is, they form a close molecules, the van der Waals force increases, so it changes from gaseous state to solid state. For that reason, at fluorine and chlorine are gaseous at room temperature, bromine is a liquid and iodine is a solid. We can say that. Now if you look at the atomic radius, now you can see on the screen the atomic radii of the elements of the halogen family are smaller than the atomic radii of the corresponding elements of the oxygen family. And if you come down the group, the atomic radii and the ionic radii increases, because down the group the same thing, the number of shells increases. Now if you see The radius of the halide ion is always greater than the corresponding halogen atom. This is because radius of an anion is always greater than the corresponding neutral atom. That is the thing. That is Cl minus ion is always greater than Cl atom. This is because the halide ion is formed with the addition of one electron to the halogen atom. So when one electron is being added to the halogen atom, it attains the configuration of the nearest noble gas, due to which the electrons in the outermost shell gets fully filled. As the electron gets fully filled in the outermost shell, they repel one another. The repulsive forces increases. And as they repel one another, the atomic size increases. For that particular reason, an halide ion is always greater than the corresponding halogen atom. We can say that. The members of the halogen family, due to their small size and high nuclear charge, have high ionization enthalpies. They have got high ionization energy. Got it? Due to the small size and high effective nuclear charge, we can say that. Got it? Now, next is halogens have only one electron less than the stable noble gas configuration. In order to acquire the noble gas configuration, halogen have maximum tendency to accept an electron, and their electron gain enthalpies are therefore high. I said you just now to you, I explained you about it. Now, next is if you see, by virtue of the high electron gain enthalpies, halogens have a strong tendency to gain electrons and act as a powerful oxidizing agent. Alright, they act as a very powerful oxidizing agent. Being strongly electronegative, halogens have a strong tendency to accept an electron to form anions. Alright, not only chlorine but all halogens act as a strong oxidizing agent. The oxidizing power of halogen decreases from fluorine to iodine. Noted this, oxidizing power of halogen decreases on going from halogens, that is from fluorine to iodine, we can say that. Alright, now halogens, that is they have very reactive element. Alright, very reactive element. In fact, each halogen is the most reactive nonmetal of its particular period. Alright, what I said you, each halogen is the most reactive nonmetal of its period. Fluorine is the most reactive of all the halogens. The reactivity of halogens decreases on moving down the group from fluorine to iodine. Now, what is the reason for the high reactivity of halogens? Why halogens are highly reactive? This is due to two factors. One is due to low dissociation energy. The dissociation energy involved in the breaking of halogen bond in halogens molecule is much lower as compared to other bonds. Alright, and the second is that the high negative electron gain enthalpy. Since halogens have very high negative values of electron gain enthalpy, hence they have got a strong tendency to gain an electron. This makes them highly reactive. Alright, this makes them highly reactive in nature. Alright, now next is coming to the color. All halogens are colored. The color darkens on coming down the group. As we know, fluorine is a pale yellow, chlorine is greenish yellow, bromine is reddish brown, and iodine is violet. Again I repeat, fluorine is pale yellow, chlorine is greenish yellow, bromine is reddish brown, and iodine is violet. The color of halogens is due to the fact that their molecules absorb light in the visible region. This leads to the excitation of the outer electrons to the higher energy levels, which you have studied in CFT. Since the size of the atom increases from fluorine to iodine, the excitation energy involved in the process decreases. Definitely less amount of energy will be required to remove an electron from iodine than in fluorine, we can say that. So thus the small fluorine molecules absorb high energy, because I said you less amount of energy is required in iodine than in fluorine. So fluorine requires more energy, high energy. So hence violet light, got it? So absorb violet light, high energy molecules, got it? That is small fluorine molecules absorb high energy violet light and show the complementary yellow color. Always a complementary color is being released. Got it? The energy which is being released, it is having lower energy because higher energy is absorbed, and that due to which a complementary color you are getting it, which is nothing but you can say pale yellow. While larger iodine molecules absorbs low energy. Alright, that is yellow and green radiations to show a complementary color which is violet. So violet is having higher what I can say, that is nothing but energy, so that it is having the lower wavelength. So this is why the color of halogens darkens on going down the group, we can say that. Now due to their high electronegativities, all halogens are typical non-metals. They are typical non-metals, we can say that. That is, due to a decrease in electronegativity down the group, iodine exhibits a smaller metallic character. Alright, again I repeat, due to the decrease in electronegativity down the group, iodine exhibits a slightly metallic character in the sense that it has a metallic luster and has a tendency to form mono positive and tri-positive ions under specific conditions. Iodine forms mono positive and tri-positive ions, that is I plus and I3 plus under certain conditions. Got it? Now fluorine also exhibits fluorine exhibits an oxidation state of -1 in all the compounds, while other halogens exhibits an oxidation state of +1, -1, +3, +5, +7 in all their compounds. The reason is that halogen atom contains 7 electrons in the valence shells. So fluorine is the most electronegative, so hence it has got a -1 oxidation state, which is most common. Alright, so due to which it can gain only 1 electron. But other elements, due to the vacant d subshell, to the presence of vacant d subshell, what you find is that ns and np electrons gets what you can say excited and reaches to this particular, what you can say, this vacant d subshells. It gets excited, and due to which we are having first excited state where oxidation state is +3, second excited state oxidation state is +5, third excited state oxidation state is +7. But in case of fluorine it is not happening, because in fluorine we don't have the vacant orbital in its valence shell, vacant d subshell in its valence shell, we can say that. So it is unable to excite its ns or np electron pairs. Got it? In case of fluorine, thus fluorine is unable to show higher positive oxidation state. So hence fluorine exists in -1 oxidation state, and already I said you it is highly electronegative in nature. Due to that reason only it has shows only a particular oxidation state, that is -1, while other elements due to lesser electronegativity shows an oxidation state of -1, +1, +3, +5 and +7 also, we can say that. Now next is that is it has got halogens possess low melting and boiling points. The melting and boiling points increase on moving down the group. Got it? Why it increases on moving down the group, the melting and boiling points? Because the strength of the van der Waals force existing between their molecules also increases. In lighter elements, fluorine and chlorine of the group, these forces are very weak. While in the heavier elements of the group, as you come down the group, the van der Waals forces are stronger and increase in going from chlorine to iodine. This is why bromine is a liquid, iodine is a solid, and they possess increasingly higher melting and boiling points. Got it? Increasingly higher melting and boiling points, so to say. Got it? So that is the what you can say is that if you see the halides, I have already said you that halogen combines with the elements present in the periodic table except helium, neon, argon and krypton to form large number of binary compound called halides. Got it? Large number of halogen combines with different metals under suitable conditions to form large number of halides. The ionic character of these metal halides decreases in the order fluorine, that is fluorides, then chlorides, then bromides, then iodides. Ionic character decreases in this order. Fluorides is having the maximum ionic character, then chloride, then bromide, then iodide. Alright, the halides, that is I mean to say the iodides is having the least ionic character and the fluorides is having the maximum ionic character. The halides of the metals have low ionization energies and are ionic in nature and possess high melting and boiling points. On the other hand, the halides of metals having high ionization energies, low ionization energies are ionic in nature. That is example alkali metals. While the halides of metals having high ionization energies are covalent in nature and possess low melting and boiling points. In case of metal exhibiting more than one oxidation state, the halide is the higher oxidation state is more covalent than the one in the lower oxidation state. For example, SnCl4, PbCl4, SbCl5 are more covalent than SnCl2, PbCl2, SbCl3. Got it? So most metals have their higher oxidation state in the fluorides. Most metals like WF6, that is your that is nothing but tungsten hexafluoride, OSF6, osmium hexafluoride, etc. We can say that. Whereas non-metal halides, that is halogens combines with non-metals under suitable conditions to form their halides, and the non-metal halides are covalent in nature. Got it. So the metallic strength of the non-metal halides decreases in the order from fluoride to iodide. That is, non-metal fluorides are very stable, whereas non-metal iodides are least stable in nature. Hydrogen fluoride is a low boiling point liquid, mind it, while all other hydrogen halides are gaseous at room temperature. That is HCl, HBr, HI, they are gaseous at room temperature. HF is the most stable among all the hydrogen halides. It is the most stable. The thermal stability decreases from HF to HI. That is, HF is the most stable, then HCl, then HBr, then HI. The reason is that the thermal stability of the hydrogen halides from HF to HI is due to decrease in the HX bond strength. The bond strength decreases. Why? Because the bond length increases, due to which the bond strength decreases. And hence, the thermal stability of fluorides, hydrogen fluoride, is more than the hydrogen iodide. Due to this reason only, hydrogen fluoride does not show any reducing character, while hydrogen iodide has a strong reducing agent, because the bond strength is less, so it can lose hydrogen atom very easily. So the reducing character of hydrogen halides increases from HF to HI. The reducing character of hydrogen halides increases from HF to HI. HF bond is a very stable bond and does not dissociate easily to release hydrogen. Alright, this is why HF does not show reducing character. Alright, so lesser the bond dissociation energy of HX bond, more easily it dissociates in the aqueous solution, and greater is the acidic strength of hydrogen halide. Again I repeat, lesser the bond dissociation energy of HX bond, more easily it dissociates in the aqueous solution, and greater is the acidic strength of the hydrogen halide. The bond dissociation energy decreases from HF to HI. Got it? So HF is the strongest bond and requires maximum amount of energy to get dissociated in the aqueous solution. This is why HF is the weakest of all the halogen acids. HF is the weakest of all halogen acids, we can say that. So acidic strength of the halogen has the order, you can see it on the screen. HI is greater than HBr, is greater than HCl, is greater than HF, we can say that. Clear? So this is about some of the properties, some of the characteristics of the halogens family, so to say.